What do you call two monkeys that share an Amazon account? Primates. Okay, so today we were talking about exponential growth, and exponential growth and decay are really just an insane concept in general. We see exponential growth and decay in life, in bank accounts, in interest, either debt or we're gaining money in interest. That can go either direction. We see it in the decaying of minerals over time, things like that. But it just is insane. The numbers get large really fast. So first thing that we're going to do, I'm going to take this piece of paper, and I'm going to pretend that this piece of paper, it's very thin, but I'm going to pretend that it's 1 millimeter. If there was something that we could picture that was smaller than that, and I could picture it in my mind, I'd use it. But anyway, pretend that this paper is 1 millimeter in thickness. In fact, it is much smaller, but that's okay. If I fold this paper in half, so now there are 2 layers, then it is 2 millimeters thick for the sake of our conversation, 2 millimeters thick. If I fold it in half again, now I've got my 2 millimeters and 2 millimeters, so I've got 4. Okay, if I fold it in half again, I've got my 4 and 4, so 8. If I fold it in half again, now I've got 8 and 8 is 16. You guys know how many times you can fold a piece of paper? This is actually a Mythbusters video. What was I at here? I had 16 and 16. I'm at 32. Okay, so this is exponential growth. It's growing exponentially by factors of 2. If I could fold it again, I've got 32 plus 32, so 64 layers. So let's see if we can write an equation of that. And I'm going to have to unfold this because it was my notes. So if we were going to write an equation for what we just looked at with the folding piece of paper, if I'm trying to relate my x's that I'm plugging in to the y's that are coming out, what we might notice is that all of these are powers of 2. That we've got 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and so on. And in fact, if we go backwards, we know that anything to the 0 power is 1, so that first one could be written as 2 to the 0 power. So if I was wanting to write an equation for this particular situation, I know that I'm always raising 2 to a power, and then if I want that power to be my x that I'm plugging in, I would just have a 2 to the x power. What's insane about exponential growth is that if we are doubling over and over, at first it doesn't seem like it is doubling very quickly. The number is not rising very quickly for that thickness. But then eventually, if we could fold a piece of paper, say like 10 times, that means we would be looking at 2 to the 10th power, which is 1,024 millimeters, which seems pretty crazy that it could get that thick, which I realized it really wasn't 1 millimeter to begin with. It was thinner than that. But that exponential growth is powerful because you're doubling it every time. So at some point, it's going to be getting large really fast. So to give us a different perspective and maybe putting some money to this is the way to make more sense. Pretend that you've got this magic genie is going to appear in the middle of your kitchen. I don't know why. You're making some mac and cheese and now you've got a genie. He does not take wish requests. That's just not how he operates as a genie, but he gives you a choice. You can either receive $1 million, or for 1 month, he's going to give you $1 on the first of the month, $2 on the second, and it's going to double, $4 on the third, $8 on the fourth, and so on. So after the first 4 days, you have $15. Okay, so you're deciding which one you're going to choose, the $1 million or the second situation, which we're probably thinking, well, obviously the way that you put this, the second situation is going to be larger, but do we really think that? Make your decision. So this is going to look similar to the paper folding. The only difference is that whenever I am raising 2 to a power, I'm actually 1 less because there wasn't a 0 day. So when I'm looking at this being 2 to the first, I actually plugged in 2 and my exponent ended up being a 1. So my exponent is 1 less than what it should be. So my equation here is going to be a y equals 2 to the x minus 1. So that way, whenever I'm plugging in 4, I actually raise 2 to the third power to get 8, and so on. But other than that, very similar to our first equation. So if we wanted to know how much you would make on the 30th day, I don't know what month this is, so maybe it only has 30 days. Maybe it's February and only has 28. But on the 30th day, you would make 2 to the 29th power. We'd plug in 30, which would be, here at the bottom, $5,536,870,912. This is not the total amount of money. This is the amount of money that you would make on the 29th day. Okay, so the total that you'd make after 30 days, which you could get with a summation or literally adding them all together, but it did it for us. The total that you would get after 30 days is $1 billion, and I'm not going to say that whole number. It's insane, is what it is. By doubling, which we don't see that happening in the first, 10 days, but eventually that number that is doubling over and over is doubling something huge. So if this if this 536 million is what you're making on the 30th day, that means on the 31st day we're making double that. So if your month has 31 days, then you're making $1 billion on the 31st day, which makes a total of 2 billion numbers, lots of numbers. So your $1 million versus billions of dollars. That's what we're looking at. And that's one little picture of why exponential growth is so powerful. And that was just doubling. We weren't even talking about tripling or quadrupling anything. So what we're talking about in this video, so that's just our general picture of what exponential growth or we didn't look at decay, but exponential growth looks like. Now let's go ahead and look at a graph. So just like anything else that we have looked at before, we will get a general parent function for our graph, and then we will look at how it shifted, how it's reflected over the x and y axis, steeper and less steep, just like any other parent function aside from, we did look at some particulars for rationals and polynomials, but kind of going back to those shifting rules. So for 2 to the x, we already have a decent picture of what this looks like because in our first two situations, we were raising 2 to a power to get different values. So if I'm raising it to the first, to the second, to the third, we can see that it is going to rise exponentially. What we might need to be reminded of is what happens when we plug in a negative number. So if I have 2 to the negative first, remember, anytime I have a negative exponent, I can move that from the numerator to the denominator or vice versa and make it a positive exponent. So this 2 to the negative first is the same as 1 over 2 to the positive first, or just 1/2. So at negative 1, I get this 1/2. If I plug in a negative 2, same thing is going to happen, where I get 1 over 2 to the second, or 1 over 4. It's even smaller than that, and I'm rethinking the marker that I chose. But what's going to happen here is that the further that I go left, negative numbers, it's just going to get closer and closer to 0. There's nothing that I could ever plug in for x that would give me a value of 0 or lower in this situation. Now, if I had a negative out in front, or you've got some different shifting things going on, then sure. But for our parent function, we're just looking at it being very close to 0 and then exponentially growing as x gets closer to infinity. So think about that paper folding, that as we go off to folding it infinite amount of times, that eventually this almost looks vertical because of how much it is exponentially growing. So technically we do have a horizontal asymptote here at y equals 0. So that would be what growth looks like. But we also have situations where we are raising a number to a power, or we've got an x in our exponent, where it actually isn't going to grow. Because in this case, whenever I'm raising 1/2 to the second power, I end up with 1 to the second power over 2 to the second power, which is 1/4. My raising it to the first would just be 1/2. Anything raised to the 0 is 1. So we can see with our positive numbers that it's actually getting smaller. The y values are getting smaller. So we've got this 0, 1. It looks like I've got tick marks on here, but then the actual graph. So ignore the actual graph, I guess. I'm counting by halves with the graph. So I've got 0, 1, my 1, 1/2, and 2, 1/4. So they're getting closer to the x-axis. In this case, if I'm plugging in a negative, so if I have 1/2 to the negative first, so like a 1 to the negative first and a 2 to the negative first, I would actually need to flip it to get the positive exponent. So I've got a 2 over 1. And same thing is going to happen when I plug in a -2. I end up with negative exponents for both, which means that I've got a 2 to the second over 1 to the second, which is 4. So kind of the opposite thing happens as what happened with growth. So let's see, then I've got a -2. Okay, so in this case, we call this exponential decay, which we're going to summarize both of these here in a minute, the general shape and what's going to happen with it. In this case, from left to right, we start up high, and now we're getting really, really close to 0. You can think about the depreciation of the value of a car. As soon as you drive a car off the lot, if it's brand new, it's going to jump down in price, what it's worth immediately, and then slowly over time it becomes less and less valuable until now, okay, it's 30 years old, and so it's not worth a whole lot, it's not running well and all of that. We still have a horizontal asymptote at y equals 0, because again, there's nothing that I could plug in for x in this situation to end up with 0 or something less than 0. Okay, so to summarize our growth and decay, so in general, our growth, we're looking at this f of x equaling a times b to the x. If we're looking at growth, we're looking for b to be in between 0 and, greater than 1. Because if my b is greater than 1, that means, I'm raising 2 to higher and higher powers, 3, 4, and, they can be decimals and all of that as well. But as long as it's greater than 1, then when I'm raising it to higher powers, it is growing. In general, it's going to look like our parent function, where we go through the point 0, 1, we're close to the x-axis, and then increase from left to right. With decay, we're looking for that b value to be in between 0 and 1, so if it's a proper fraction, then whenever we raise it to higher and higher powers, it is actually getting smaller. It's still going to go through that 0.01 because anytime I'm raising it to the 0 power, I am getting out 1. And it will decrease from left to right. Both of them have domains of all real numbers. I can plug in any value for x, but their ranges for the parent function are from 0 to infinity, not including 0 because there's that horizontal asymptote there. There are other cases where we can see that growth and decay switch. So let's look at a few, just deciding whether they are growth or decay. Why don't you go ahead and pause the video and sorry, I'm working on it. Pause the video and see if you can decide whether you have growth or decay for these. Okay, so starting with the first one, I have this 0.25 raised to the x, that's a 1/4. It's in between 0 and 1, so that is definitely decay. As I raise it to higher powers, that's just going to get smaller. For number 2, I'm looking at the base that's being raised to a power, so in this case my base is 3. It's going to triple every time, so this would be growth. Now I do have this 1/2 on the outside, and that is going to make it less steep compared to just 3 to the x, but it is still going to grow. It's just going to be a less steep growth. For 3, same situation. I'm looking at the base, not the number out front. It is going to make it steeper than another function that's just a 3/5 to the x, but because my base is in between 0 and 1, it is going to decay. And then my last one is kind of a trick question. I've got my base is a 4, and so normally that would be growth, but then I also have my x is negative. So remember, anytime I have a negative power, that means that I could move it to the denominator and make it positive. So if I attach just that -1, so these would be the same, 4 to the -1 times x, or to the x, but they would be multiplied. Then I could move my 4 to the -1 to the denominator and make that power positive. So my 4 to the -x is actually the same as 1/4 to the x. It is the same as number 1. So these are actually the same thing. What we would have to know, we'll look at looking at those rules that we have used before, reminding us of rules, that initially I might graph this as growth. So knowing that it gets larger from left to right, it increases. But then remember, anytime I have a negative with the x doing what the x is doing, it reflects over the y-axis. So it will actually end up looking like decay. So we could either use our transformation rules there, or we could change our base to where that negative is being attributed to the base. It is a fraction. Okay, so let's look at graphing a few of these. They're going to shift just like anything that we have done before. We just have to look for those shifting rules. So remembering that my left and right shift is going to come from what's happening with x. It does the opposite of what we think. My up and down shift is going to come from what is outside of what's happening with x, and it's going to do what we think it would. Remember that we had that horizontal asymptote that was at 0. That is usually an easy thing to start with, that it was at 0, but we're shifting down 4, 3, 4. So that means that our horizontal asymptote will now be at y equals 4. I know that since I have the x plus 3, it will be shifted to the left 3. But then also remember, whenever I was plugging in 0 earlier, I got that point 0, 1. And so now, since I've shifted it down, now that point is at -3. And so whenever I shift to the left 3, it's going to be at -3 and -3. So it's always 1 above that horizontal asymptote, and then left or right, however many we're shifting left or right. Oh, whoops. Hopefully you guys caught me as I did that. I just went for it once I had my point. This one is not growth. Make sure we're looking at, we just talked about it, our base to decide whether we're looking at growth or decay. Since my 1/5 is in between 0 and 1, this is a decay, and so I should be starting up and then getting closer to the x-axis, or to that horizontal asymptote. Sorry about that. I do want to label my 1 point that is always going to be 1 above the horizontal asymptote and then shifted left or right, however it needs to be shifted. So that's my -3, -3. But then the rest I am sketching based on my shifting. Okay, so let's look at another one. Oh, sorry, we'll do this one first. Okay, so first, shifting our left and right, up and down. So we are shifting up 2, and that's where my horizontal asymptote will be. This one did not shift left or right, but it does have this negative out front, so we're going to go ahead and sketch it and then see what that negative does to it. So I didn't go left or right. That point is always going to be 1 above my horizontal asymptote. Looking at my 3, my base, I can see that it is growth, and so initially I might think it looks something like this. But then I do have a negative on the outside. If we go back to our parabola is the easiest to look at, I think. If it's negative on the outside, it reflects over the x-axis. Since we already have this asymptote, we might be wondering whether we reflect all the way down here or just on the other side of the asymptote. Remember, you can always plug things in and see what happens. So if we plug this 0 in for x, our negative 3 to the 0 power, or sorry, 3 to the 0 power is 1. The negative's on the outside. So we have a negative 1 plus 2, which is 1. So it is just going to reflect right over that asymptote. It will be symmetrical about the asymptote. And I get this question a lot, whether we would call this growth or decay now that it is flipped over the asymptote. I don't have a word for it. I mean, technically it is decreasing, but we don't really see this happen a whole lot in the real world. As far as sketching our graphs, we do want to be able to use our rules to sketch them, but this isn't something that we need a name for. That point right there is at 0, 1. Okay, so last one. This one's got an E in it. If we remember from Algebra 2 that E is like pi, it is a letter, but it actually represents a specific number in math. So E is like 2.718 something. So just knowing that it is a number, that it is greater than 1, so that will affect, I know that it is growth because that E is greater than 1, or at least initially it's growth. I've got that negative x up there, so that is going to be challenging there. It's going to do something different to it. But let's start with our up and down shift that we are shifting down to. And then initially this is kind of like the radical, the negative under a radical, where it seems like we should be shifting to the left 3, but then that's negative, so I'm not really sure if I should be shifting to the left or to the right. So what might be helpful is to go ahead and plug in a negative 3 or positive 3 and see what happens. And we can see that being able to plug in a positive 3 is what will get us a 0 in the exponent. So we're raising e to the 0 power and getting 1, and our 1 minus 2 being a negative 1, which is where we wanted that point that we are using to shift. So it is actually going to be at a positive 3, negative 1. And then because of that negative in the exponent, it will end up looking like decay. So initially this is going to tell us growth, but then because I have that negative in the exponent, it's reflected over the y-axis, and so it will end up looking like decay. If we're not sure, we can always plug something in and see, okay, if I plug in 0, I would have e to the 3rd, which is going to be a large number, a minus 2. So this is a big number, whereas if I plug in 4, I would have e to the negative 1st, which is 1 over e, small number, minus 2. So it would end up being closer to that horizontal asymptote at negative 2. Okay. So don't overthink it. We're using our shifting rules, decide growth or decay. A couple of those had a few little exceptions and things that I would like us to know, but we're looking really basic graphs today.